Good morning. My name's Chet Sandberg. I've been in the electric heater business for over 40 years, and I'm going to share with you today some of what I consider the most exciting technical advancements that have come along in the last few years. I'm a consultant to MCAAA, which is a MI cable producer in the UK. Arthur Hale, the other author, was at Shell with me when we did the initial work for the Piceance Basin in Colorado, converting oil shale into oil. This is the matrix of thermal applications in downhole environment. Cold production is used for lighter oils and heating is not usually needed. Cyclic steam stimulation, or huff and puff as it is sometimes called, heats the near wellbore with steam, reduces the viscosity, the steam is turned off, the reduced viscosity oil then drains back into the well and is produced through the same well that the steam was introduced. Steam-assisted gravity drainage usually has two horizontals. The top horizontal steam is introduced, creates a bubble and some pressure, reduces the viscosity, and oil is produced through the lower of the horizontal wells. The same can be done with electric heaters. You'll put an electric heater in the top well, and then it can produce the reduced viscosity, which is then produced through the bottom well. Also, there are some interest in using this electric heaters in the top well before steam is introduced, so you can save a lot of water by introducing electric heat in the top to get it to the temperature you need before the steam is introduced. So there's a dual usage now possibility for electric heaters in SAGD applications. Viscosity reduction is used on a worldwide basis. Electric heaters do this. There's been both the polymer insulated heaters and the mineral insulated heaters. Polymer insulated heaters are used for temperatures usually below 300 or 400 degrees F, and then you have to go to the mineral insulated inorganic insulations for higher temperature and higher powers. You can use electric or steam for in situ vis braking. There's been some papers on that. You can also use in situ upgrading process, which has been developed and patented by Shell and used both in the Peace River area for a project they called Viking, and also in Colorado for the Piceance Basin in the Mahogany project. There's also electric heating used for flow assurance, both in offshore applications and in onshore applications. And you can do various different power levels depending on whether or not you want to use a polymer or an MI cable. This is an example of electric heaters in the Santa Barbara area, the Santa Maria Valley. It was leased by a company called Hancock. In the 1980s, they used steam, and if you look at this chart, you can see that the water produced is in the blue, the oil produced is in the green, and gas produced is in red. So the well was active from 1982 till 1987 with significant amount of oil and gas produced. Then it produced minor amounts, but then an electric heater system for cyclic operation was introduced in 2006, and you can see that the quantity of oil produced was increased by a factor of 3 or 4. The green line goes up to 1,000 barrels a month, I think this is, and the gas went up to 500 equivalent. But the interesting thing to note here is that there is no water production with the electric heater, and in the California areas where the oil is produced, not producing water, which is a toxic waste, is a real advantage. This is a sample of averages of some of the wells in the Bakersfield area where electric heating was used. The previous chart is one of these wells, and you can see that the increase over production without a heater increased 410%. You also see that there was no water produced, which is interesting because there was water produced in the production without heating. So this shows that there's a very interesting opportunity here to produce without producing water, which, as we said, was a toxic waste in the California area. This is what I call the electric heater matrix. It's a combination of the mechanical and electrical properties of the heating systems. Electrically, we have two types of circuits. We have a parallel circuit and a series circuit. The power is given in a parallel circuit by V squared, the voltage squared divided by the resistance. And for a series circuit, it's given by I squared R, which is the current squared times the resistance. In the parallel circuit, there are multiple current paths, and in the series circuit, there's a single path. Then on the vertical axis, we have two types of heaters. We have a temperature source, and we have a power source. The temperature source is like boiling water. You always know where what the temperature of the water is going to be. The power source puts in a fixed amount of power per unit length of heater, but you don't know what the temperatures are. So the independent variable on the temperature source is the temperature, and the independent variable on the power source is the Q, or amount of energy put in. It's almost like the difference between boiling an egg and frying an egg. So you have the temperature source with the boiling, and use a 3-minute egg, so you know what the the heat transfer is going to be. And for the power source, you fry an egg, and you always have to look at it. And in these cases, they both have two downsides. The temperature source, the problem is that the temperature around the heater gets too hot, and it doesn't put out the power you want. And in the power source heater, the quantity of heat going in keeps raising the temperature until it burns out. What we're going to be talking about here is the lower right red square of the power source heater in the series circuit, which is MI cable, and we're going to be talking about heaters that are up to probably 1,500 to 2,000 meters. Here's a picture of some MI cables that are now being produced for applications in downhole environments. The instrument cable is interesting because it has 5 jackets on it. The 4 internal jackets were for strength member. This was a 13,000 foot long logging cable, and the outside was a corrosion protection jacket. It was single conductor, but it was used in some geothermal logging. The other 2 are what is being produced now for downhole applications for heating, and they're being used in a number of places, both in Alberta and other places in the world. The 0.85 inch cable can go to 3,000 feet long, and the 1.2 inch cable can go like to 2,000 feet long. We have magnesium oxide is a white powder. The center conductor is either copper, or it's the alloy which is used for the heating. We want to have low losses in the overburden, but have significant losses in the heated section. And we'll talk more about that, the comparison of voltages, which is really the key advantage here that we're finding in these heaters, is that they can run at much higher voltages. Here's a schematic of an MI cable. It's got the internal copper or alloy conductor, which conducts the current and does the heating. It's got MgO, magnesium oxide, which is a very good electrical insulator, but it's also a very good thermal conduction agent. Usually a good electrical insulator is not very good at thermal conduction. MgO is used in a lot of different heating elements. For instance, the heating elements on your stove, electric stove, will probably have MgO in it. Then we have possibility of 2 alloys for the outer jacket. One can be a strength member in the middle, and one can be a corrosion member on the outside. They're usually welded at 180 degrees, so you have some redundancy there. And so what we're looking at here is large diameter MI cables that can also run at much higher voltages. And that's the key to which we're going to talk about in the next slides, and the advancement that we're talking about today. But first, let's talk about the viscosity for a bit. This is just some graphs of what viscosity change as a function of temperature. The lower left graph there The real world viscosity there I have put, and sometimes in the Alberta bitumen you can get up to 100,000 centipoise, and even a slight 50 to 60 degree increase in temperature will reduce it to the pumpable level. The Lloydsminster area also has heavy oil, but it doesn't have quite the absolute top values of the viscosity, so it can also be used for electric heating. Also can be used to increase the viscosity there. So now we have a comparison. The heaters we're talking about today, and the advancement is the fact that you can run a heater at 4160 volts, which is much higher than the 600 volts. And if you look through the specifications that have been in the past, IEEE specifications and vendor specifications, they don't want you to run MI cable over 600 volts because of the possibility of arcing within the MGO. However, the technology is now available that you can run at 4160. These are usually three-phase systems, so you usually get the voltage divided by the square root of 3, and in that case you'll be running the 4160 in the 22 to 2700 volt range. And we can see here the real reasons that we are so excited about this technology. The length of the heated section for a 600 volt heater can be typically 250 feet for 144 watts per foot. But when you run at 4160, you can get up to 2,000 feet at the operating temperatures of 400 degrees C. Also, you look at the loss in the overburdens. For the specific heater calculated here, the 600 volt heater will lose half of its energy in the overburden, and you don't really want to really lose a lot of energy. It just costs money and doesn't do any good on the viscosity reduction in the formation. But when you use 4160, you only lose 11.8% of the heat of the energy in the overburden. Also, the estimated weight of the three cables is much less. You can get 5.3 pounds per foot for three cables for a 600 volt system, but you only have 3 pounds per foot for the high voltage, because the I2R heating can have a smaller diameter resistance element and a smaller diameter copper in the overburden. So the bottom line here is that the total system power can be different depending on what you use for the voltage. And in the previous example, the 600 volt system had a total power of 225 kilowatts, and the 4160 had almost a megawatt of power. It had 953 kilowatts. And you go down through this, and when you look at the cost of heating the formation, the power cost is the bottom number here. The power cost per foot of the heated formation for 600 volt heater is $720, whereas the cost for the 4160 volt heater is $381. And so that's the operation hours per year. So this is the cost of operating per year. And so what we're doing is we're getting a lot more heat into the system at a much lower cost. I'd like to thank everybody for listening to the presentation, and now I'm open for questions.